So in this next part, we're going to be talking about properties of big O. So in particular, we're going to be talking about how we can prove those properties. So I'm going to describe a variety of different properties that big O has, and we're going to see how we can prove those statements using the definition of big O. So many of the techniques I've shown you in the past will be very helpful here too. So you're going to find that a lot of the ideas and sketches for these proofs very often rely on your intuition for how you can prove basic big O claims. But here's the catch though. This is the big catch. These claims are going to be about arbitrary complexity functions. So they're not just, oh, n is big O of n squared. It's not a claim like that. It's going to be that, oh, I give you two complexity functions. You don't know what they are. They can be arbitrary. So they have certain conditions they may have, but the point is that you don't know what fixed complexity function they exactly are. So we're going to talking about a variety of these. So you're going to find that a lot of the proofs I'm going to give you almost operate like a blueprint or a skeleton for how you might prove other big O claims. And sometimes you could even apply it to simplify down some claims. For example, in a previous session, I've talked about the idea that the transitive property of big O can be used as a shortcut in some of the proofs I've shown you before, for example, in smoothness. So here's the first claim. So what I'm going to first talk about is that big O is reflexive. So it has what we call the reflexive property. Now you may not have ever heard of this term reflexive before. Here's what it means. Given any complexity function f, you could say the following. You could say that f is big O of f. So if you've never heard of this term, and you might ask, why is it called reflexive? Well, I like to almost look at it like you're looking at a mirror. So if you have the thing you're studying, and you ask the question, does the thing have the property? That's what reflexive usually means. So if I'm looking at the mirror and I'm asking, do I have the property? In terms of big O, if I give you a complexity function, the answer is yes. So I could just say, for example, that n is big O of n. I could say that n squared is big O of n squared. I get that for free from this property. So we're going to prove this next, and I will tell you up front that it's going to be probably the easiest proof we're going to do here for the properties. So the first thing you need to know is that we're dealing with a statement about any complexity function. So normally when we phrase a proof like this, we need to make sure that we're talking about any complexity function f. That's the first thing I need to point out, that the length is a little bit different than just any one fixed complexity function. So I need to kind of pin one down, but I'm going to give it a name. Consider any complexity function f So if I want to show that f is big O of f, what should I do? Well, what did we do last time? Well, what we did was we used the definition of big O, right? That's one way you could do this. So naturally, I'm just going to use that. And what's the game plan? The game plan is to find the two constants c and n0, right? So if I can find those two constants, then I can invoke the definition of big O, and then we're done. That's going to be about as simple as it gets here. So then, to prove the claim, we find constants c, which is a positive real number. That plus is getting a little long for my taste there. And n0, which is a positive integer. So that for all n greater or equal to n0, it has to be that f of n is less or equal to c times f of n. Well, but here's the catch here, right? we need to write it out like this. Sorry, I'm getting really excited here. Well, the minute you write this out, you see f of n is less than or equal to c times f of n. What's the easiest constant I could pick here to make it so that this is in fact equal? So what can I do to make this a little simpler for myself? Well, what I can do is I could just assign c to be 1, and then I have f of n is less or equal to f of n. And you know the left-hand side has to be equal to the right-hand side because it's the same thing on both sides. So this should remind you of some of the first examples we did. So I'm going to pick c is equal to 1. Then you observe. Then observe both sides of the inequality are equal. Implying f of n is less than or equal to f of n holds for any n greater or equal to n0. Remember, n0 is just some positive integer, right? So all you have to do now is you just kind of tip this over, you just pick n0. You can pick any n0 here and it works. So I'm just going to choose n0 is equal to 1. Therefore, so if you find yourself looking at this and you're like, for any n greater or equal to n0, now you know n0 is a positive integer, right? Now if you're really just like, okay, Dan, but I want to really put a number here, you could just put 1 right here and that's perfectly fine. It's easy enough for you to convince somebody that two things that are equal on the same sides, that it will be that it doesn't ever differ, right? Because it's an equality. It's an equation. Therefore, it's not just they're not going to differ in their values. Therefore, by the definition of big O, so now I just pull out that big O definition, we can say that f of n is big O of f of n. And we're done. Piece of cake, right? So big O is reflexive. So just to remind you what that means that like n is big O of n. So you don't have to like, this property says that, yeah, you basically just say this. And the proof gives you the why. So notice that this explains to you, it's not an explanation, it's actually an argument. It gives you the why. So you can think of it like an explanation, but it's a formal argument, right? So if anybody asked you, well, why is that the case? You could just show them the proof, right? So in fact, if you gave me any claim of like n is big O of n, or n squared is big O of n squared, you could just straight up use this proof and plug in your functions and it should work. This is how and why, when we get a general statement like this, you should be able to just use this as a blueprint for any such claim. So if I give you n squared is big O of n squared, because this is for any complexity function f, all you have to do is you should be able to just say, whoops, I see there's extra parenthesis here. Sorry, there's a little bit of fun there. You just put n squared here, and you just put n squared everywhere you have f of n, or f. You just put n squared everywhere, and this should all work. So anyways, that's the reflexive property.